Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder why studying the best and brightest doesn't always tell us how to become great ourselves? This new paper has a fascinating answer. This paper dives into how studying only top performers in fields like chess or athletics might be tricking us. Imagine trying to learn to bake by only studying Michelin star chefs. You might miss the crucial early steps and beginner mistakes that actually lead to baking skill. That's kind of what this research is about. We often look at the experts, the grandmasters, the world champions, and try to figure out what makes them so good. But the researchers here argue that focusing only on these elites can actually mislead us when we're trying to understand how anyone becomes an expert in the first place. Think about it. To even be studied by these researchers, you have to have already succeeded. You've already made it to the top. This means you're already filtered by success, and success in any field is usually the result of many different things working together. So the researchers say that the things that seem important when we're looking at the very top performers might not be the same things that help them get there. And they might even be misleading when we look at people who are just starting out or are in the middle of their journey. The core idea here is selection bias. It's like when you're picking teams for a game and you only pick the kids who are already really good at sports. You might notice that within that group of super talented kids, certain skills don't seem to matter as much as they would in a group with mixed abilities. Maybe a kid who is super tall but not a great shooter still makes the team because their height is enough of an advantage. But without that height compensation, a less skilled shooter in a mixed group might not make it. This creates a trade-off that only exists because of the selection process. They explain this using something called collider bias. Imagine two things that help you get to the NBA, for example, height and shooting skill. Both are good, but if you only study players who are already in the NBA, you might find that height and shooting skill are negatively related. This doesn't mean being taller makes you a worse shooter. It means that to make it to the NBA, a shorter player has to have exceptional shooting skill to compensate for their lack of height. While a taller player might get in even with average shooting, the selection process of being in the NBA has created a misleading relationship between height and shooting skill. To show this, they use a cool example with young chess players. They looked at intelligence, accumulated practice, and chess skill. In the whole group of kids, they found that both higher intelligence and more practice were linked to better chess skill. They were also positively related to each other. But when they looked only at the top 20 players by chess skill, things got weird. Intelligence and practice started to look negatively related. Among the best young players, those who were smarter tended to have practiced less, and those who practiced more tended to be less smart. This is a trade-off that selection created. It wasn't an inherent relationship in the whole group. Plus, the strong link between practice and skill weakened significantly when they only looked at the top players. Beyond this collider bias, the researchers point out a few other ways selection can mess with our understanding. One is range restriction. When you only look at the top performers, you're looking at a very narrow range of skill. This can make any apparent relationships between skills and performance shrink towards zero. Imagine only measuring people over 6 feet tall. The variation in height is now limited, and any correlation between height and, say, basketball skill will be weaker than if you measured people of all heights. Another issue is sampling variability. Elite groups are often small. When you have a small group and the signal is already weakened by range restriction, random chance can easily make a weak positive effect look negative or vice versa. It's like trying to guess the majority opinion of a large crowd based on the opinions of just 5 random people. And then there is sequential selection or survivorship. Before you even define who the elites are, many people have already dropped out. Think about a sports academy. Many kids might start, but only a fraction make it to the professional level. This initial attrition filters the group even before you set your elite criteria. This means the adult sample, especially the elite part, is a heavily filtered group. To really test this, they're not just looking at existing data, they run computer simulations. They created a model with 2 gates. The first gate represents kids who stay in the game as adults, and those who drop out. The second gate selects the top performers from the adult sample to be considered elite. They wanted to see if a process where early specialization does help performance could look like it harms performance when you only look at the elite adults. In their simulation, they set it up so that early specialization helped youth performance. But adult performance depended on youth performance and other later developing factors. When they applied the 2 gates to this simulated data, guess what happened? The relationship between early specialization and adult performance became weak or even negative within the elite group. This happened even though in the underlying model specialization was still helpful. This is a crucial finding. They tested scenarios where early specialization had a weak positive effect on adult performance and another where it had a weak negative effect. When they looked at the elite groups, their simulation showed that these 2 scenarios produced almost indistinguishable patterns. This means that if you only study the elites, you can't tell if an early predictor is genuinely helpful, harmful, or just appears that way due to selection. Their simulations show that the elite cutoff really matters. The more extreme the cutoff, meaning the fewer people you include as elite, the more distorted the relationships become. They found that you would need an incredibly large elite sample, something like 5,000 people, to reliably distinguish between a weak positive and a weak negative effect. Most studies of elite performers have much smaller sample sizes in the range of 50 to 100 participants. To see if this holds up in the real world, they looked at longitudinal data from chess players and female 1500-meter runners. They tracked players from a large youth cohort into adulthood and then looked at the elite performers. Just like in their simulations, they found that better young performers were much more likely to remain observable as adults. In chess, about 38% of players rated by age 14 still had a rating at age 20 or later. In running, only about 7% of young athletes recorded a time after age 20. This confirms that the adult sample is already selected for better youth performance, even before you define elite. Then they looked at the relationship between youth performance and adult performance within these adult samples. In both chess and running, they found a strong positive relationship among all adult survivors. But when they narrowed it down to the top 10 adult performers in each field, that positive relationship reversed. In chess, the link between youth rating and adult peak rating became negative among the top 10. In running, youth and adult time showed a negative correlation among the elite. This is the key empirical evidence matching their simulation. The pattern of positive relationships among survivors becoming weak or negative in the very elite tail was present in both chess and running, despite their very different developmental demand. This suggests that selection bias might be a widespread explanation for these controversial findings about expertise. So what does this mean for researchers and for us listening to scientific findings? The authors propose a framework. First, researchers need to be clear about what they want to learn. Are they interested in predicting who will do well within an already selected group, or are they aiming for broader developmental insights about how expertise develops from the beginning? Second, they stress the importance of defining the initial cohort and mapping out all the gates or selection processes that occur. Third, and this is crucial, they suggest researchers should show how their results change depending on how elite is defined. This could involve graphs that show the correlation at different cutoff points. If the results dramatically change based on the cutoff, it strongly suggests selection bias is at play. Finally, they say researchers should match their claims to the sample. If you studied only elite performers, your conclusions should apply only to that specific elite group, not to the entire population of aspiring experts. They also suggest statistical methods that can help account for selection bias, like inverse probability weighting or using negative controls. But the primary takeaway is that good study design is key. Understanding and accounting for selection processes from the start is more effective than trying to fix it afterwards with complex statistics. So what is my take on this? This paper presents a really compelling argument for skepticism when we hear about counterintuitive findings in elite performance research. The idea that studying the best might actually obscure the path to becoming the best is a powerful one. It forces us to question whether apparent developmental reversals are real shifts in how excellence is achieved or just statistical artifacts of who gets studied. The implications here are huge for coaching, talent identification, and even for how we motivate ourselves and others. If we're always looking at the finished product, the elite performers, we might be ignoring the broader, more nuanced, and perhaps more generally applicable lessons about growth and development. The paper doesn't say that selection doesn't play a role or that developmental pathways don't change, but it strongly argues that we can't assume they do based only on data from elite samples. We need better designed studies that follow individuals from the very beginning to truly understand the journey of expertise. What do you think about this idea of selection bias in expertise research? Does it change how you view findings about top performers? Let me know in the comments below. And if you found this breakdown helpful, please give it a like and subscribe to RUBIN'S Mind Lab for more science insights. See you next time!